Hi, I'm Carrie Laboski. I'm a professor of soil science and a statewide extension specialist in soil fertility and nutrient management. Today we'll be discussing soil acidity and liming. So what is soil pH? Well, it's a measure of soil acidity. Soil acidity is important because it affects many chemical and biological reactions within the soil that then influence plant growth and nutrient availability. Agricultural lime can be used to neutralize soil acidity when it becomes too great, when it becomes a problem for crop production. The schematic here on the bottom shows an analog scale of soil pH. You can see that acid soils are considered those that have a pH less than 6. Alkaline soils are those with a pH greater than 7. And from a soil standpoint, neutral soils are typically considered 6.5 to 7.0. So if you remember back from chemistry class when you were in high school, soil pH is pH itself is a measure of soil acidity. Acid soils have more hydrogen ions than they do hydroxide ions, and that's specifically within the soil solution because those are the ones that get measured for pH. And if we look at this little equation here, this should also look familiar to you, where pH is equal to the negative log of the hydrogen ion activity in soil. As we think about soil acidity, there's some different types of soil acidity. One type is the active acidity. That's the actual hydrogen ions that are in the soil that we're measuring. And if we look at this schematic here of a poultry watering system, the active acidity is the water that the birds would actually be drinking. And reserve acidity is another type of acidity. This is the potential acidity that exists in the soil. And aluminum can be a factor within that potential acidity. It's also represented here as the reservoir where we have the reserve acidity. So as active acidity is neutralized, reserve acidity can come back and fill in to become active acidity. Now, pH buffering is a really important component of soils. Soils are really highly buffered, or can be highly buffered, and that means that they can resist a change in pH. So as soils naturally become a little bit more acid, the soil can buffer that drop in pH, but also upon liming, soils take a little more effort to get the pH raised because of this buffering capacity. Increases in the buffering capacity increases or decreases with changes in soil cation exchange capacity, which is influenced by clay content and organic matter content. So again, soils that would be considered weakly buffered are those where the pH is easier to change, and they tend to be sandier soils with low organic matter content. Our strongly buffered soils are ones where the pH is much more difficult to change. Not saying that it can't be changed, it just takes more effort and more lime to change that pH. How does the soil become acid? Well, there's several ways. Use of acid-forming fertilizers, many of our nitrogen fertilizer materials, will acidify the soil. Also, when we look at the removal of base cations, so calcium, magnesium, potassium, when they are used by the plants or leached out of the system, it leaves more room on the soil cation exchange to hold hydrogen ions. So older soils tend to have more basic cations leached away and have subsequently a lower pH. Now, the third way where soils can become acid is through respiration by plant roots. That's acidifying the soil environment right around the root. Now, there are several beneficial effects of liming. Improvement in crop yield, availability of nutrients, improved microbial activity in the soil. That also is related to legume fixation and also the addition of calcium and magnesium, which are needed nutrients for crop production. Here's an example of what low pH can do to a crop, and that liming is beneficial from a yield standpoint. This is a field in eastern Wisconsin where the soil pH is below 5.0 in that area where we have no corn growing. And you can see that there's kind of an area radiating out from that has reduced crop height. And this is a field, again, where soil pH was below 5 in that particular area, and then it was moving into adjacent areas in the low 6s. So just an isolated pocket where it had become quite acid, and you could see that it's not favorable for corn production. Now this graph is showing the effect of soil pH on crop yield response. On the left axis here we have the fraction of maximum yield, and on the bottom we have soil pH. This data was collected from studies conducted here in Wisconsin. We're looking at alfalfa, corn, and soybean. And we could see with corn here in the green line at the top that we have yield reductions when the soil pH is below 6.0, and then it flattens off. That pH is above 6.0. Doesn't matter, you don't get any yield improvement from having better pH or higher pH compared to 6. Now for soybean and alfalfa production, soybean's the blue and alfalfa is the red, we can see substantial yield losses from having lower soil pH levels. And in particular alfalfa, you can see how much yield loss really is occurring. And that's why we have for our legume crops higher target pHs where we'd like to maintain the pH level. Here's a chart showing you the relationship between pH and nutrient availability in the soil. So just to look at nitrogen, for example, you have the wider the area is on any of these nutrients, that's showing that it has more availability, and a narrower area like over here shows that it has a little bit less availability. And the bottom here is the different soil pH levels. So that we can see that for most of our crops we're going to want to be growing them at a pH between 6 and 7, and you can see we have pretty much the maximum availability for most nutrients within those ranges. It's also important to note some things here in the micronutrient area, that as the pH moves above 7, many of our micronutrients decrease in availability. The one exception to that is molybdenum, where we have greater availability of molybdenum at pHs over 7 compared to much lower pHs. Now, calculating the lime requirement of soil, how much lime to apply, you need to know a few things. So one of them is your target pH of your soil. And it's important to maintain the pH of a field for the most sensitive crop in the rotation. That is the most pH sensitive crop in the rotation. So if we look at our target pHs for our various crops here in Wisconsin, this is not an extensive list, it's just some of our more common crops. You can see that alfalfa has the highest target pH of 6.8. Our legumes are also higher, and then we move into our grass crops, corn and wheat, they have a target pH of 6. Now, when we measure the soil pH, how do we determine when is it time to lime? Well, what we do is we look at the soil pH, and if it is more than 0.2 units less than the target pH, that says it's time to lime. So if we have alfalfa growing in the rotation and our pH is 6.5, that says, okay, that's more than 0.2 units less than 6.8, therefore it's time to lime. Now, the one thing we have to keep in mind with lime requirements is that when we look at the target pH, we look at each crop, but we look at the whole rotation as well. So if you have a rotation that's alfalfa with corn or corn silage, alfalfa has a pH of 6.8 and corn is 6. Well, you want to maintain for the most sensitive crop in the rotation. So you want to be maintaining that pH at 6.8. You don't want to drop it down for the corn years. It's not necessary. You can keep that maintained higher. Now, how do we calculate lime requirement? Well, it requires a couple things. So we need to know the soil pH. We also need to have a measurement of reserve acidity, and that's what we use a buffer pH measurement for. The CaCO buffer is the one that we use here in Wisconsin, and typically the higher the pH, the buffer pH value, the less lime is needed to change soil pH. So that means a high buffer pH means it's a weakly buffered soil, so you don't need quite as much lime. And this chart here, this is showing just the different lime recommendation equations depending on the target pH for your rotation. And in Wisconsin, we have a large number of different target pHs because we grow a variety of crops here in the state that have a wide range of target pHs. So we need to have some flexibility for that. And just to look at one of these equations at the target pH of 6.8 on this bottom line, it's very simple to use. You just input your buffer pH value here and your soil pH value right there, and then you just essentially plug and chug and you get a number out, and that's your lime recommendation. But we do have to keep in mind that we have to make some adjustments to these lime recommendations. Because these equations here on this slide, they're not super precise at low lime recommendations. So that means it is possible to calculate a negative recommendation. And that doesn't mean there's anything wrong with the system, it's just there's imprecision at those low rates. So what that means is that if you've already determined you need lime, so your buffer pH is more than 0.2 units less than your target pH, that says you need lime, but you have determined that the recommended lime rate is less than 2 tons per acre by that equation, then you should apply 2 tons per acre on medium and fine textured soils. So just to reiterate a different way, on medium and fine textured soils, if you happen to calculate a lime rec less than 2 tons per acre, the recommendation is 2 tons per acre. So there's essentially floors and ceilings. Now on coarse textured soils, we have a different floor. And so if the lime rec is less than 1.5 tons per acre, then the recommended rate is 1 ton per acre. Now, we do have some ceilings on these recommendations, and the upper end for most situations is 12 tons per acre. That's the top. It's possible to calculate higher recommendations, but they're not realistic. And then even a 12 ton per acre rate, many folks would be applying a couple applications of lime rather than one. And then if you're in a potato rotation, it's really important to not to cap that at 8 tons per acre, because potatoes with scab, the higher the pH, the more problems you could have with scab. So we don't want to overlime potato. So keeping that potato rec at 8 tons or less. Now, we also have some adjustments to the lime recommendations if you're no-tilling. And this is a feature of our lime recommendation system that many people don't know about or disregard. And so if you've had no-till management for more than 5 years, okay? So why we say more than 5 years is it takes about that long a time to start developing a bit of stratification in soil pH with the depth. And so what you do is then you'd sample, instead of a normal 0 to 6 or 0 to 8 inch soil sample for lime, you'd take a separate sample that's a 0 to 2 inch sample and measure the soil pH. And here, if the pH is more than 0.2 units below the target pH value, there's just a flat recommendation of 1 ton per acre. And that's because in these no-till systems, there's no way to incorporate the lime. It's all going to be surface broadcast, so it's just going to be a lower rate that needs to be applied to neutralize that acidity in the surface soil. Now we do have some additional adjustments to these recommendations based on the depth of sampling, or we'll call it plow depth. So, if you sampled up to 7 inches deep, there's no adjustment for the lime recommendation factor. But if you start tilling deeper into the soil for deeper incorporation, you would adjust the lime recommendation upward by multiplying it by one of these factors. And that's just because you're incorporating lime into a greater amount of soil. You want to make sure there's enough there to neutralize all of the acidity. Now, we have materials with different neutralizing indexes, or NI, here in Wisconsin. And how we deal with that is we have a little equation to do this conversion. So we take our lime requirement of the material that we want to use. Let's say it's 80-89 lime. And I should back up. Our recommendations here in Wisconsin, most of the time you're going to see them for 60-69 lime. Sometimes you'll see them for 80-89 lime. But let's say you have a recommendation for 60-69 lime, but you're going to use 80-89 lime. So you need to convert this. So you would take the recommendation for and that's what LR is, lime requirement or lime recommendation for 60-69 lime, and multiply that by 65 and then divide by the neutralizing index of the material that you're going to use. So if it was 80-89 lime, you'd put 85 here in this equation. And that's just simply to convert it, because materials with higher neutralizing indices have, you need less of them to make your change in soil pH. So that moves us into discussing liming materials. And there's several components of liming materials. So the first component is the fineness factor. And this photo here shows several mesh sizes that are used. And this is part of the process of determining the neutralizing index of a lime. We need to know the fineness. And so the lime itself is put on a series of sieves. And this is an 8-mesh sieve, and you can see the size of the lime particle that is retained on top of that 8-mesh sieve. Here's a 20-mesh sieve, and this is the amount or the size of particles that will pass through 8 mesh but are retained on 20. Now at the bottom is a 60-mesh sieve, and this photo doesn't show it very well, but that's a pretty fine mesh. And what we're seeing here in these particle sizes is what will pass through the 8 and through the 20 mesh sieve, but then is retained on the 60 mesh sieve. And then we do have material that will pass the 60 mesh sieve. So this is really fine, powdery type material. And you can see that as you look at so these little piles of the lime material. So as we're assessing a liming material, we look for the fineness, and this is the fineness factor. And this graph is showing how long it takes, so time in months, how long it takes for lime once it's applied to change soil pH. So we've got the time in months versus soil pH. And you can see that we have 100 mesh sieves, so that was much greater than, or much finer material than what I showed in the last slide. We get very quick reaction, and in less than a year we've really increased the pH a lot. We get down to, say, a 20 to 30 mesh sieve, we can see that we've increased pH some within 12 months, and it flattens off a bit. And then some materials like this 8 to 20 mesh, slow increase in pH and just continues over time as those particles are broken down. So remember, liming, it takes some time for it to react with the soil. It's not an instant change, and if you're looking at rotations, specifically like alfalfa, where you have a crop that likes a higher pH, you want to make sure you're liming enough in advance of that hay crop to get the soil pH up where it's going to do best. Now, to actually calculate the fineness factor, what we do here is we have our screen sizes that we showed on that previous slide, the meshes, and here's the analysis. So just an example of what percentage of the lime that was put on, a sample of lime. It's here 5% was retained on top the 8 mesh sieve, 25% was retained on top the 20 mesh sieve, and so on. And then here we have an effectiveness factor for each of these screen sizes. So if we have materials, those bigger chunks, the greater than 8 mesh, they have considered not effective liming material. So you get a 0. We get down to that really fine stuff, which will pass the 60 mesh sieve. That's considered as 100% effective. So it's a factor of 1. And so what we do is we multiply the percentage of that lime sample that will pass through a particular screen, and we multiply it by its effectiveness factor. And that's what we're doing here. We're just looking at the fractions and their effectiveness factor, and we tally them up at the bottom. And here we get 67. So that means our fineness factor is 67 in this particular example. Now we have to move on to the purity of the lime, because it's not just all about how fine it is, it's how pure it is, how much calcium carbonate equivalent we have. And so remember, calcium is not the liming agent here. The carbonate is the liming aspect. So we need to know how much carbonate equivalent we have. And this chart is showing a variety of liming materials that we have available here in Wisconsin. What is the neutralizing agent in them? So for dolomitic lime, it's important to keep in mind that dolomite is calcium and magnesium carbonate. Something like paper mill sludge is mainly calcium carbonate. Calcitic limestone obviously is calcium carbonate. Then you get materials like wood ash, where we have potassium, calcium, and magnesium carbonates all together. And here on the right, we have the calcium carbonate equivalent of the pure material. So we look at calcitic limestone, and that is considered 100%. That's where the 100% area is set at. You can see that dolomitic lime is actually somewhat more effective than calcitic lime because it has a higher calcium carbonate equivalent than calcitic lime. When we look at byproduct type materials, wood ash would be an example. It can be anywhere from 20 to 90% calcium carbonate equivalent, so highly variable. This is where you really need to have some of these waste product limes tested to know what you have before you use it. And it's a good use, secondary use of these materials to prevent them from going into landfills or other kind of disposal situations. Now, actually calculating the neutralizing index as we do here in Wisconsin. Before I get into this, it's a good place to remind folks that how the neutralizing index or the effective neutralizing power or there's different names for neutralizing index in different states. They're all calculated often a little bit differently, so you really need to know what's going on. So if you are in southwest Wisconsin and you're getting lime, not that you probably need much lime, but if you were getting some lime from somewhere in Iowa, you might see some different terminology because they're using the terminology that's used in Iowa. So you just need to double check with what you have to make sure you know what you're getting. Now, the neutralizing index here, so it's a measure of the lime quality, and it's very simple. We take that fineness factor and we multiply it by the purity factor. So pretty easy. So if we have a soil that has a calcium carbonate equivalent of 90% and a fineness factor of 67, we just take 90 times 67, and that gives us 60.3. So that says that our neutralizing index is 60.3, and that would be classified as a 60-69 lime. Now, if you'd like more information about soil pH and liming, there are a few resources available. Chapter 5 in Extension Publication A2809, or Chapter 6 in Publication A3588. Both are available at the Learning Store for free PDF downloads or purchase.